thing. I printed out this little last packet of notes so that you don't have to write down every single thing. Please add to them as needed. Notice the problems are not worked on there. So that's going to be kind of for you to complete. And in fact, most of the notes that we are doing now are going to be more problem-based from the here out. Today we're going to be doing what's called limiting and excess reactants. We're also going to be calculating theoretical yield and percent yield equations. So we'll try to get through all of that today. Tomorrow we'll do one last thing, but it's pretty easy, and it's just recognizing exothermic and endothermic. And then if there's any calculations with it, we'll kind of do them together in class. But that's kind of where it is. My plan is also to start giving out the study guide for chapter 2, for test 2, which again is covering chapters 5 through 8. And then we should be able by the end of class tomorrow, we should be able to answer all of the chapter 8 active questions. All right. Today you're going to get through a good bulk of them. There wasn't a lot. Even yesterday's material didn't help us get very far in active because there's some specific things you have to know. Moving forward, my plan is on Monday to review chapters 5 and 6, Tuesday to review 7 and 8. I'll probably do it in those single pagers like I did last time. I'll make some questions that look similar to the test questions that we're going to answer in there. I am playing with the idea that we will do a practice test that I might even set it up through Performance Matters or something like that so that you can see a grade immediately, see what you did and all of that, and then we'll discuss the most missed answers, questions, and things like that. So from there, and then Thursday will be the test, and then Friday I'm starting chapter 9. All right. So we have, after we finish chapter 8 today, we have 4 more chapters, 9, 10, 11, and 12, and they have to be done. I mean, everything has to be done by May 10th. Now, I know there's some AP testing that falls in there, LEAP testing falls in there, so we're going to have to figure out the final what days work for who. I may even have to have 3 different days during LEAP testing that y'all come in, that some of y'all that from different periods come in at different times. I got to figure that out for the final. Test 3 is not going to be as big of a deal. We can get that one done. It's just the final is going to be kind of catchy. All right. So, looking at today's material, the outcomes for today. So we are still going to be doing stoichiometry. Nothing's changing about the format of it. The only thing that's going to change today is a little bit about the prompt. When you look at the prompts for today, you're going to notice instead of just having one given, they give you 2. So you have 2 different starting points, but you want to go to the same ending point. All right, so you're going to have to actually do 2 problems for each one and see which one is the right answer. All right. So we're going to describe a method for determining which of 2 reactants is a limiting reactant or which one puts limits on the reaction. Calculate the amount of moles or mass in grams of a product. Given the amount of moles or masses in grams of 2 reactants, which one? And so one is in excess. And then distinguish between theoretical yield, actual yield, and percent yield. And then calculate the percentage yield based off of the actual yield and the quantity of the reactant. All right, so going back to yesterday's work. So open up your POGL. Let's look at number 35 and number 36. If you didn't do number 36, I apologize because I don't think I actually assigned it in this period. But we'll go ahead and go through it and look at the setup and all. All right. So for number 35, we had boron oxide and then we had boron oxide plus magnesium reacts to form magnesium oxide and boron. So the first thing that was asked us to do was calculate the molar mass of boron oxide. So just double check. I got 69.62 grams per mole. The other thing that I went ahead and did, because I knew I was going to need it later, because I needed boron. Remember that boron, we can look that, since it's just a singular element, there's no molar mass to calculate. You just look it up off the periodic table. Boron's 10.81 grams per mole. All right, so the question says, how many grams of boron can be obtained from 234 grams of boron oxide? So I'm starting 2, 3, 4. Boron oxide. What's the first step I need to do? All right, what are we trying to accomplish by doing that? Get to moles. That's what I'm looking for. All right, so I want to get to moles of boron oxide, and so I'm going to divide it by the molar mass of it, 69.62 grams of boron oxide. So that allows me to get rid of the grams. Now I'm in moles. So now I'm in moles of boron oxide. What is my next thing that I'm going to try to do? I need to get to moles of boron. So I need to get rid of B2O3 and go to mole of B. All right. Where am I going to find my relationship between boron and boron oxide? From the balanced equation, the coefficient. So I'm looking here and I'm looking here. So it's 2 to 1. And then, so now I'm in moles of boron. So what's my last step that I'm trying to do? Trying to get to grams. All right, so I want to be in grams of boron. So I need to get rid of moles of boron. So for every 1 mole of boron, 10.81. All right. How many sig figs should our answer be in? 3. And so what would our answer be? I got 72.7. All right, check your rounding. Make sure you use the same numbers. If you used a little bit different on your rounding, you might have a slightly different number. All right, any questions about that one? So again, just pay attention to what's canceling. Now, I'm going to tell you this because I saw it in active. Pay attention on your given. So remember, molar mass, we can go grams to mole. On active, there's one that starts off in kilograms. And so you have to go from kilograms to grams first before you can go to grams to mole. All right. So that one, just make sure you're paying attention to what you're starting units for. I wouldn't be surprised if they do something like that on the test where they start in kilograms just to throw you off to see if you're paying attention. All right, so make sure you're reading questions all the way through and all of that. All right, so same chemical reaction. We're starting with 40 grams of boron. We're trying to get to mass of magnesium. So 40.0 grams of B. First step is to get rid of grams and go to moles. So 1 mole of B is 10.81 grams B. Now I can go from mole of boron to mole of magnesium. And so I look at my reaction, it's 3 to 2. And then for every 1 mole of magnesium, I look at the periodic table, magnesium is 24.31. So what do we get for mass of magnesium here? Still should be 3 sig figs, 135. All right. So hopefully you're recognizing that we did a lot of these calculations in chapter 6. It's the same types of calculations. We've just taken it and doing, instead of doing one at a time, we're doing 2 or 3 at a time. All right. So it's the same things. We just have to pay attention to setup. All right. I'm sorry to say there's no generic formula I can give you for this. You do have to build the equation as you go. All right. So that's why I gave you the little tool of the spider. But again, I want you to get to a point that you can write it down. And I mean, I've tried as we went through the notes to show you a little way to memorize it. You know, you just do mass, volume, particle, and mole in the center. All right. And as long as you can remember the relationships, you should be able to figure out what you have to do if you have to multiply or divide. All right. So now, doing number 36, like I said, I forgot to assign it. But if we balance this, you should get 2, 2, 3. If you want to go ahead behind me and verify that, just double check. So in this one, it says balance and determine the mass of N2. So I'm looking for trying to get to grams of nitrogen produced from the decomposition of sodium nitride, 100 grams of sodium nitride. So I'm starting in grams of Na, N3. My first step is always to get to moles. So I want to get to moles of Na, N3. Now that I'm in moles, I can get to mole of N2, and then I can get to grams. The things that I'm going to need is I need molar mass of N2. Nitrogen is 14.01, so 2 times 14.01 is 8.02. And I need the molar mass of NaN3. So I have 1 sodium at 22.99 and 3 nitrogens at 14.01. And so I get 65.02 for my molar mass of that. So now we can just plug things in. If you haven't set this one up already, go ahead, try to set it up based off the information that I've given you, and then I'll come back and write it all in as we're going. All right. So, a couple of things to remember. Remember, for molar mass is always relating to 1 mole. So whatever your molar mass is related to 1 mole of that substance. So we're starting out with NaN3. So 65.02. Over here, grams of nitrogen, 28.02. And then coming up right here, I need to look at my balanced equation. So I have 3N2 for every 2 NaN2. My answer should be in 4 sig figs. And so what do we come up with? 64.64. So the other sheet that I passed out at the end, I asked you to try to do those. I'm not going to spend as much time on these. I'm just going to kind of show you the answers so that you can check. All right. So question said, how many grams of iron 2 oxide must be burned to give 100 grams of CO2? So I don't know why I did a D. I just was doing that for extra stuff, I think. So we should have ended up with 90.91 grams of iron 2 oxide when we set this up. So the big thing is checking your ratio, that there's 2 moles of iron 2 oxide for every 8 moles of CO2. Is that the right one? Does that match what y'all's sheet is? Yeah, I rounded to whole numbers. So as long as you're right around that 90, you're good. That was just me being lazy. All right. Going through for the other page, we had these other 2 problems. So one was a volume problem, one was a molecules. I didn't give us any examples with molecules, but hopefully you were able to figure that out. So I'll talk about that one. All right. So first thing we had to do was balance the equations. So one of the things, and I didn't tell you this, but methane is one of those things that's always a gas. Carbon dioxide is one of those things that's always a gas. So those are just ones that normally it'll tell you that it's a gas, and we can just assume. All right, so it says, what volume of methane is needed to completely react with 500 liters of oxygen? So I'm going to treat 500 liters as 3 sig figs, so I'm going to keep my answer to 3 sig figs at the end. So I have 500 liters of oxygen. Oxygen is a gas, so I can divide by 22.4 to get 2 moles of oxygen. Then I set up my mole ratio, that is 1 mole of methane for every 2 moles of oxygen. And then I multiply by 22.4, which gives me 250. Now, I do want you to notice something that happens in gas stoichiometry when you're going volume to volume. Mathematically, what's happening right here? What are those 2 doing to each other? Canceling. So this essentially, so all we really have to do is multiply it by the mole ratio. But I want you, like if inactive, you have to show the work. When on the test, I would show it, but just realize when you plug it in the calculator, you're just doing that. All right. Now, for I'm gonna I stopped at mass on this one because apparently I told the students last year to change it to mass, but I'll finish it out. So it says how many molecules of carbon disulfide react with 4.21 times 10 to the 19th molecules of oxygen. So the key thing is recognizing this first step. We're in molecules, we have to divide by Avogadro's number. All right, that gets us 2 moles. Then we can do our mole ratio. All right. Now, the question that y'all had, so you would have gotten a slightly different answer because your question asked you to go to molecules, right? All right, so let's look. The only difference here, instead of doing molar mass of CS2, we would have done now. I think I know why. I know why I did that last year, because here it would have had that cancel out situation again. That all you would have had to do was divide this number by 3 to get your answer. All right. So so again, just remember, I'm not so much worried about the answer on this one as I am that you recognize if you start off in molecules, you got to divide by Avogadro's number. If you start off in grams or anything else and it asks you to go to molecules, you multiply by Avogadro's number. That's going to be the biggest thing. So if you just need to know the answer to check, all right. So if you just need to check your answer for molecules, it should have been 1.40 times 10 to the 19. All right. So I get 1.40 times 10 to the 19 molecules. All right. Questions on that? If not, let's go ahead, jump back into the notes. All right. So 2 definitions that I want us to have. A limiting reactant is the reactant that limits the amount of product. All right. So not arguing whether you do the speed limit or not. What is the purpose of a speed limit? What is that supposed to tell you? The maximum speed you're supposed to be going on that roadway. That's on you if you want to get tickets. All right. Don't do that when you're going to Grand Isle. Golden Meadow will pop you for 1 mile. On the causeway. Neighborhood, you shouldn't speed anyway because that's dangerous. Okay, well, it's in the morning. All right. So, anyway. Oh yeah, I forgot. You live out in Months. Months is different. I just like picking on Months. Sorry.
Yeah, it's crazy. It's crazy.
I mean, my neighbor called cops on me for my speakers being too loud. So that's a whole nother story. All right. 50-year-old man, his car has too much boom in it, I guess. I don't know. Toyota Camry. Understand that. All right. All right. Anyway, limiting reactant limits the amount. So another way to say this, limiting reactant is going to tell us the maximum amount of product that we can have. Now, understand in this situation, the maximum amount of product is going to be a smaller number than what the other one produces. Because if one limits, that means we can't produce as much as the other one says we can. All right. So the other term is excess. If you have an excess of something, what does that mean? You have too much or more than you need. All right. So excess reactant is the substance that's not going to be completely used up. So if I have carbon plus oxygen, and I want to react it to form carbon dioxide. And just balancing that balances like that. Everything's 1 to 1. All right. Now, notice that in my molecular diagram, I'm saying I have 5 carbon atoms here. I have 10 molecules of oxygen. So essentially, I actually have 20 carbon atoms. How many, to make carbon dioxide, how many oxygens do I need for each carbon? 2. So my carbon limits how much carbon dioxide I can make here. I have excess oxygen because I can only make 5 carbon dioxide molecules because I only have 5 carbon atoms. I have plenty of oxygen. So notice that I have carbon left over. So I have carbon remaining. And so I have 5 molecules of extra carbon. Ideally, if we wanted to use everything up and have no extras, I would need 5 carbon atoms and 5 molecules of oxygen. But because I only have 5 carbon atoms, I can only use 5 of those oxygen molecules. And then the other 5 are just left over. They're just remaining. So y'all kind of understand that concept, that something's going to produce extra, the other one is going to be used up. All right. So another definition is listed in there, theoretical yield. Based on our math, the theoretical yield is how much we can produce mathematically. So theoretical yield it's going to be a mathematical answer that we get using a stoichiometric equation. All right. So theoretical yield is how much can I produce mathematically. So if I had 5 moles of carbon, and I want to know how much CO2 I can produce in moles. And then I had the chemical reaction that we just had before, carbon plus oxygen reacts to form CO2. I could do my little equation, even though we should be able to just see the answer here. But 5 mole of carbon. So for every 1 mole of carbon, I have 1 mole of CO2. So that means I can produce 5 mole of CO2. All right. So because it's a 1-to-1 relationship, it's going to be the exact same amount. If it was a 1-to-2, it would be half as much, things like that. And we'll see that later. But theoretical yield is what we get with our stoichiometric answer. All right. So that's our definition. So let's look at an example problem. So now I have my reaction of silicon dioxide reacting with 4 moles of hydrogen fluoride gas reacting to form silicone tetrafluoride gas and water. All right. My prompt says if 6.0 moles of hydrogen fluoride is added to 4.5 moles of silicon dioxide, which is the limiting reactant. So there's actually 3 answers that we can get here. We can get limiting reactant, we can get, excess reactant, and we can get theoretical yield. All right, so the question's only asking for limiting, but we're going to answer all 3 because you have to do all the work to get all 3. All right, so what do you notice different about this prompt than the ones that we've done the past 2 days? Got 2 different starting places. All right. Now, it didn't tell us where to solve for. All right. So I'm not going to compare this to this and then this to this. What I'm going to do is I'm going to pick one of my products that I want to solve for. So looking at this, which product would you prefer to solve for? Water. And I pretty much know students are going to pick water. Water is the more familiar compound. All right. So that means I'm going to have an A and a B equation. So I'm going to call HF my A equation. I'm going to call SiO2 my B equation. That's different from the A and B on our mole sheet. So I probably should say 1 and 2, but my brain always goes this way. All right, so when we look at this, I'm starting off 6.0 mole of HF, and I'm starting off with 4.5 mole of SiO2. Now, they were nice to us. They were nice to us and gave this to us in moles. So all I really have to do is a mole-to-mole relationship here. So now we want to compare and we want to solve for the same thing. So we said that we're going to solve for water. So notice that I'm solving for the same thing on both of them. So when I look at this, I have 4 moles of HF for every 2 moles of H2O. And looking at this one, I have 1 mole of SiO2 for every 2 moles of this. All right, so listen to the question that I'm going to ask. We're looking for the limiting reactant or limiting reagent. Reagent, reactant's the same thing, just different terminology, different word. Which one of our reactants, hydrogen fluoride or SiO2, which one will run out first? Hydrogen fluoride. So because this one produces a smaller amount, that makes this my limiting reactant. So I'm going to write, if it asks me for a limiting reactant, I'm looking for a compound. All right. Which one's going to have extra at the end based off of these calculations? SiO2. So this is my excess because it theoretically can produce a higher amount. All right, so now, what is the maximum amount based on these givens? What is the maximum amount of water that I can produce? All right. So remember, what's going to happen if I try to make 9 moles of water? It's going to run out of HF. So the maximum amount I can make is 3 moles. So this is my theoretical yield. So if it helps you to think, about when you're doing a limiting and excess problem, you're going to pick the smaller answer. If it's asking you for the theoretical yield and you're doing limiting and excess, you're going to pick the smaller answer. If it's a regular stoichiometric problem and it asks you for theoretical yield, you just do it the one time through and answer it. If it gives you 2 givens, you have to do it both and you pick the smaller of the 2. All right. So again, it's not anything different mathematically than we were doing. It's just asking you to pay attention to some things. As you get to higher levels of chemistry, I mean, we essentially did it right here, but as you get to higher levels, there are some tricks you can do to shorten this, but it serves no purpose for me to teach that right now because it'll serve to confuse you in the future. All right, so let's look at this next one. I've already kind of set this up for you in your thing, so I want you to take a minute and I want you to try to solve this one and see what your answers you get, and then I'll pull in mine. All right.
Wait, hold up. Let me go get it.
Now, just some things to kind of help you. All right, so first thing, that was all that was on there. I don't even know why I did that. All right, so when you read this problem, it says if 18.1 grams of NH3 is combined with 90.4 grams of CuO, it asks for what is the theoretical yield of nitrogen. So the first thing that I need us to recognize is this one told us what product it wants us to go to. So we're looking for the theoretical yield of nitrogen. So that means on this one, we're looking for grams of nitrogen ultimately. And so the reason why I went 2 grams is because I started in grams. All right, the last one, it started in moles, so it was okay for me to answer it in moles. All right, now going through on that one, that means also here I'm solving for nitrogen. So you're always going to have to solve for the same thing. So if I'm trying to get molar mass of nitrogen, 2 times 14.01 is 28.02. So this part of the problem.
Wait, why did you get 28? Why did I get 14?
In 2. Because N is diatomic, so there's 2 nitrogens there, so its molar mass is 2802. All right, now
1 mole is
1 mole of N2. Each nitrogen is 14.01 So I have 2 of them. 28.02. All right. Now, so the next part I can set up is I can set up my mole ratios. So from ammonia to nitrogen is 1/2. Nitrogen is 1. So I'm going to look here. CuCO is 3. All right. I'm starting off at the same place. So I have 18.1 grams of NH3. I had 90.4 grams of CuCO, or CuO, sorry. Now, hopefully I'm not throwing you off by putting them over 1. That's just, I mean, anything over 1 is that number. All right. So this part really doesn't matter. I was just doing it so it's fractions all the way across, just so we can kind of get used to seeing that. All right. Now, what am I missing? Molar mass. So molar mass of NH3 is 17.04. Molar mass of CuO is 79.55-ish. All right. So now I go ahead and solve. For this one, that's funky. I didn't even write down the answers. I mean, I wrote down the overall answer. All right. All right. So, based off the information we get, which one of these is our limiting reactant? Which one's going to produce CuCO? Even though CuO, sorry. Even though CuO started off with a higher mass amount, it actually is going to produce the least whenever we react it. All right, so that means our excess is ammonia. What is our theoretical yield? 10.6 grams of nitrogen. All right. Yeah. Yeah, you're just comparing. You always look for the smaller amount produced. That's your theoretical yield. And then you look for which reactant produces that smaller amount, and that's your limiting reactant. Now, on the test, when they ask these type of questions on the test, they can ask you for any one of those 3 answers. All right. If it's a constructive response, they're going to ask you for the theoretical yield. If it's multiple choice, they're going to give you the choices there, and you have to pick which one produces the smaller amount. So no matter what, you still have to solve it. You just have to know that if you get the smaller number, that means this is the limiting. Large number gives you the exit. I've never seen it on the test ask for all 3 at once. I've seen it do the same reaction, same numbers 3 times and ask you in 3 different parts. But I've only seen that on the quiz. I don't think I've seen it on the actual test. All right, looking at the next one. All right, so we have a reaction between ozone, which is O3, and nitrogen monoxide reacting to form oxygen and nitrogen dioxide. And so it says, suppose 6.75 grams of O3 reacts with 7.40 grams of NO. How many grams of NO2 will be produced? And then it says circle the limiting reactant, but I'm going to ask for all 3 things because we got to do it anyway. So reaction 1, reactant 2. So now we're kind of setting this up. So go ahead, take a minute, see if you can set it up, and then we will go over it. It should already be balanced. 4 and 4. Yeah, it's already balanced. It's just all 1 to 1. All right, so I'm not going to put the answers up just yet. I'm just going to show you the setup so that you can check to make sure you set it up correctly. So looking at the first reaction, it says, so the question is asking us to get to grams of NO2. So the first step is to get from grams of O3 to moles of O3. Then I can do my mole ratio. So there's 1 mole of NO2 for every 1 mole of O3. And then NO2's molar mass is 46.01 over 1. For the second one, we're starting off at nitrogen monoxide, and we're trying to get to NO2. So I set it up 1 mole of NO divided by 30.01 grams of NO, which is the molar mass. It's a 1 to 1 relationship because the equation was balanced, all coefficients of 1. And then 46.01. Now, so when we solve this, how many grams of NO2 are produced by ozone? All right. How many grams are produced from nitrogen monoxide? All right, 11.4. So, going through the questions.
I don't know how to figure these out.
Yes. All right, guys. So going through the questions, which is our limiting reactant? Ozone. Since ozone produced the smaller amount, that's our limiting reactant. All right. Our excess is the other reactant, so our excess is going to be nitrogen monoxide. And then our theoretical yield, the maximum amount that we're going to be able to produce in this case is 6.47 grams of NO2. The reason why that's the maximum amount is I'm going to run out. If I try to produce any more than 6.47, I'm going to run out of ozone, so the reaction stops. Once you run out of fuel in your car, that's where you're at. So if you don't refuel it, I mean, your car still got, so your car, most people's car, unless you're running electric, if you have an internal combustion engine, oxygen that the car needs is readily available. It's going to get that from the air outside. The gasoline is your limiting. Once you run out of gas, you don't go any further. All right. So In this case, my ozone was my limiting. Once I run out of that, the reaction doesn't go any further. All right. So moving forward in this. Two more definitions kind of thrown out there. So we have actual yield. The actual yield of a product is a measured amount of product obtained from reaction. So for actual yield, another term for this is experimental. All right. So another name for actual yield is experimental yield. So if we actually perform a reaction, even though mathematically we think we can make this much, but in the real world we never make exactly that much. We always make a little bit less because nothing is 100% efficient. So you're always going to have something, maybe an impurity, maybe something else happened that we just don't have as much as we think, and we can't produce as much as we think. All right. So the actual yield of a product is the measured amount of product obtained from a reaction. So think lab results or actual results. All right. Percent yield is a comparison of the actual yield to the theoretical yield. So it's a ratio of the actual to the theoretical multiplied by 100. So the formula that we're looking at here to get percent yield is going to be actual yield over theoretical yield times 100. All right. Just like any percent calculation that you've ever done. So you can look at this as like a grade calculation. If your total points was 20 points and you only got 18 of them, you can do 18 out of 20, 18 over 20 times 100, and that gives you the percent score. All right. So the active for this chapter has 25 problems. If you only get 23 of them correct, you can do 23 divided by 25 times 100. That's going to give you the percent score that I'll put in the grade book.
That's the percent of you, that's a Y?
Yeah, that's a Y. I did it as a lowercase y, but it's just because my. Say again, Connor. I'm sorry. Yeah, in that one because it's 25, but that's not the reality of a percentage. Yeah. Because the next chapter is 37 problems, so it doesn't always work. Yes. Say again. That was actually something that I collected in the first quarter and that I graded early on in the first quarter. I will have to print out another one for you, or you can go back and look. That would have been chapter 4 that you would have. I think I posted it in like a PDF of it. All right. So let's look at a problem for this. So one of the things that I'm really trying to get y'all to focus on is seeing the difference in the way they ask the question as to what they're looking for. So in this one, they give us the chemical reaction between C6H6 chlorine, and then it produces C6H5Cl and HCl. All right. The prompt it gives us, it says, when 36.8 grams of C6H6 reacts with an excess of chlorine, the actual yield is the actual yield of C6H5Cl is 38.8 grams. So the first thing we have to recognize, is this a limiting reactant problem? No. So this number is our actual yield. So that's going to be part of this actual over theoretical times 100. All right. So that's going to be your 38.8 grams. So the question I have is, now, what do I do with this? I have to use stoichiometry from this to this to get my theoretical yield. So I have to solve for my theoretical yield first. All right. So when we look at this problem, you need to be able to understand, even though it's asking for percent yield, we have to solve for the theoretical first. So I'm starting off with 36.8 grams of C6H6. What's my first step? If I'm trying to get to C6H5Cl, what's the first step that I have to do here? I have to get it to moles. So for every 1 mole of C6H6, I'm going to have a certain grams of C6H6. All right, so I need my molar mass there. All right. I actually had 78.12 when I did it, but all right. So now that I'm in moles of C6H6, I can get to mole of C6H5Cl. And so I have to look, make sure it was balanced. It is balanced, so it's 1 to 1. And then ultimately, you have to check it. Just make sure you verify. If you don't see coefficients, check it. If you see coefficients there, you can assume it's balanced. All right, so now I need to get from moles of C6H5Cl 2 grams of C6H5Cl. And so for every 1 mole of that, so for my molar mass of chlorohexane, I get 112.56. All right, so now we can solve there. That's going to give me grams of chlorohexane. And that is my theoretical yield. Once I solve that, then I can take my actual, divide it by my theoretical, and that's going to give me my percent.
Wait, give me a second. What was the answer for that?
I'm asking you to solve that.
Oh, hold up. Don't give me it yet.
Don't look at it yet.
No, don't say that.
Yeah, I just went further because
So we're at 38.8.
in the problem, because I want y'all to look at the problems. All right.
Maybe I should start sleeping more classes. I just this doesn't give me time to overthink. Like when he goes over,
All right. So your kind of homework for tomorrow. Your kind of homework for tomorrow is number 3. We will start there. We'll start there tomorrow to check that. So number 3, I want you to do that one from your packet for your homework. We'll start there tomorrow. And then in active, at this point, you should be able to answer numbers 1 through 18 and 25.